Very good morning. So yesterday we have started to understand how to estimate the area under the curve bounded by the lines x equals to a, x equals to b, and x-axis, and curve y equals to f of x. Okay, and so this is your x equals to a, this is your x equals to b. So what was the idea is that you have divided this interval a to b into n non-overlapping subintervals. So by following the ordered sets, a equals to x naught and b equals to xn, and then you have identified some points x1, x2, and so on. So somewhere it is kth subinterval xk, and then this is so on. And what you have done is then you have drawn the parallel lines, what means like vertical lines, in other words. Then you have assumed some other approach known as Darboux approach, and then so you have, if you call this I is a interval a to b, which is subdivided into non-overlapping subintervals. So k is equals to 1 to n, where each ik can be identified by the following interval xk minus 1 to xk, where k is running from 1 to n, which x naught is a and xn is b. Then we have also denoted the length of the interval, length of ik. We have defined it by delta xk, which is nothing but xk minus 1. Then what we have made the assumption is that the function f defined on closed interval ab, of course we are talking about only real valued functions, is bounded. So which ensures that the set f of x such that x belongs to I, x belongs to a to b, is bounded. Means this set has both infimum and supremum. So let's say now let small m is the infimum of f such that x belongs to I, and capital M is the supremum of f of x such that x belongs to I. Okay, so since we are assuming that this is the assumption that f is bounded, so this gives you guarantee that the infimum will exist, and let us denote it by m, small m, and supremum will also do exist, and that is denoted by capital M. Right. So now with this, I can certainly say the following. From here, what we get is small m is less than equals to f of x, less than equals to capital M for all x belongs to I. Okay, so this is so sure. Okay, then we have tried to identify, so in the Darboux approach we have tried to identify the lower sum and the upper sum by means of creating the rectangles which are lies below the curve. Then we'll be calling as lower sum, and if we consider the above the curve, well, then we'll be calling as upper sum. Okay, so what is the process was? So let's say small mk, so that mk is defined as the infimum of f of x such that x belongs to ik. So since ik is a part of the I, so it is does exist. Okay, so here k is running from 1 to n. Okay, now capital Mk is defined as supremum of f of x such that x belongs to ik. So this also do exist for k is equals to 1 to n. Okay, so if you identify small mk here, so what will be in this case, if you, because mk is nothing but the infimum over this interval xk minus 1 to xk, and if I look at this graph, I don't know the function yet. Okay, so it's increasing, it has the behavior is increasing, we have seen. So certainly small mk is lies on the left hand point of the ring, right? So this is going to be small mk if I look into the graph of the function. Okay, and if you look at the if you try to identify the capital mk, it is going to be at the right end of the interval for this particular case. Okay, right. So if you have the graph of the curve like this, so then it will scenario will change if the interval in the interval it is decreasing or increasing. If you try to identify accordingly, you have to identify small mk and capital M. So with small mk, you will be able to get the rectangle. Okay, on this by using this ikth interval, and whose area is nothing but mk into delta xk, small mk. Okay, now for the case of capital mk, you are going to have this. Okay, this one. Okay, right. So you can identify. So now certainly clearly one thing is there, small mk is always less than equals to capital mk for all k. Okay, small mk is less than equals to capital mk, whatever you will choose. Okay, so now this will implies small mk times delta xk is less than equals to capital mk times delta xk for all k equals to 1 to n. Okay, right. Now since this is true for all k equals to 1 to n, so this certainly implies summation of k equals to 1 to n, small mk delta xk is less than equals to summation k equals to 1 to n capital mk delta x. Now if you recall, the left side on the left of inequality, this is we called as lower sum. Okay, and this is the right side is called as upper sum. Okay, so and we have denoted the partition P as x naught to xn. So which is certainly tells you for any partition P, the following will be always true. LFP is always less than equals to UFP. Okay, right. Now, not only this, okay, not only this. Now, if you look at the definition of f of x, so also small m is less than equals to small mk, which is less than equals to capital Mk, which is certainly less than equals to capital M. Okay, because this small m is the infimum over all for all values of on I. So it's still sitting on the left of small mk. Okay, and small mk is the smallest smaller interval then. Okay, so right, infimum is an increasing function if you recall. Okay, and supremum is going to be a decreasing function if you taking the part of it. Okay, right. So small mk is small m is less than equals to small m, less than equals to capital mk, less than equals to capital M for all k equals to 1 to n. So this will imply small m times delta xk, you multiply by delta xk, Okay, capital M time delta xk less than equals to capital M time delta xk for all k equals to 1 to n. Now, so therefore, this implies summation. If you take the summation, if you because delta xk's are positive, non-negative numbers, so this will implies m times summation delta xk less than equals to. So this summation is LFP less than equals to. This is the nothing but the UFP less than equals to capital M times summation delta x. K is equals to 1 to n. K is equals to 1 to n. Now see, delta xk is the length of ikx subinterval. Okay, and now and also ik are the non-overlapping subintervals. Okay, so this total length means means a length of I1 plus length of I2 and so on length of IN is going to be the length of I only. So if you write the definition of delta xk, okay, the negative term will get cancelled, only you will remain with m times b minus a is less than equals to LFP less than equals to UFP less than equals to capital M times b minus a. So this is, see, for any partition P, it will be always true. Okay, so LFP, whatever the partition you will take, LFP is always going to be greater than equals to M times B minus A, and certainly is going to be less than equals to small capital M times B minus A. Similarly for the case for UFP. Okay, right. Now, as yesterday lecture, we have seen, if you consider the refinement of the partition P, okay, so I have the partition, let's say P1, let P1 is the partition X0, X1 and so on Xn. Okay, and let's say P2 is the refinement, is a refinement of P1 of P1. So by adding 1 point, so by adding, let's say by adding one extra point, okay, 1 point say zk belongs to xk minus 1 to xk, okay, is obtained by this. So we have seen we have seen that in this case, if you include one more point, you have seen the following. Okay, so obviously when we are saying P1 is P2 is a refinement of P1, so we are going to denote it by P1 is going to be the subset of P2, means like in this term, means like, okay, P2 is a refinement of P1, so we are going to denote it by like this. Okay, right. So we have seen that once you add one more point, then the lower sum will increase to LFP2. Okay, right. And whereas this upper sum will decrease. So UFP2 is going to be less than equals to UFP1. Now we note that LFP2 is going to be less than equals to UFP2, right? Just now we have already shown that lower sum with the given partition P is going to be always lies below that the upper sum. So this certainly less than equals to this. So what it tells you is, when you consider the sequence of partitions, now refinement, by adding one point at each time, what you will observe is, you will observe that is going to be, okay, so I'm telling this P1 is with this simple, with P2 means P2 is a refinement of P1. Okay, so if P1 is contained in P2, contained in P3, and so on. So what we'll observe then, what will be observation is you have LFP1 is less than equals to, okay, LFP2 less than equals to LFP3 and so on. Okay, so wherever in the limiting case, anyway, okay, it's a increasing sequence, but what it there is, it's always going to be less than equals to, yes, it's going to be always less than equals to capital M time B minus A. That's so sure, that we know, right? Because lower sum always going to be bounded by less than equals to M time B minus A whenever F is bounded. Okay, so the boundedness of the function becomes the necessary condition, you can say, for the Riemann integrability. Okay, so once this sequence is increasing and it is bounded, so certainly it will converge. Okay, so converge to where? The supremum over, okay, or the supremum of this, so supremum of this set, if you consider. Similarly, if this happens, if P1 is contained in P2, contained in P3, and so on, then you have P1. Okay, so then, so this happens, and you have, this is UFP1 is going to be greater than equals to UFP2, greater than equals to, and so on. So it's going to be decreasing, but it's not going to be lower than small m time B minus A, that we have known. Surely. Okay, so above implies that the set you have, this is so this implies, okay, so this all two implies that supremum of LFP over the set with which set means like the partition. So say set where P is a partition of n, P is any partition of I, does exist. So that we are going to call as L of F, because you are taking the supremum over all the partition P of I. So this will be like in the next term, when you take the supremum, this will be, we are going to get rid of this in the limiting case, you can say. So that's why here small f only present, you cannot, with only the P will be not there, and that exists. Also that UF, which is going to be the infimum of UFP, where P is any partition of I, does exist. That's also that exist. So both things will exist, surely. For, and what we call is, so we denote LF is going to be integration A to B f of x dx, the lower Riemann integral, and u of f is equals to a this p bar f of x dx, and it is called the upper Riemann integral. Okay, so there's a notation. Okay, it's a underscore here. Okay, means it's a lower, it's the lower limit, you have the put the bar, and if you put the upper limit with the bar, then it is called upper Riemann integral. This is called lower Riemann integral, and both will exist. Okay, there's no question of existence here because this will always do whenever the function is bounded. So these numbers are always there. Okay, right. Now, what is the relation will be always there in LF and UF? Okay, that always be there. Okay, so if LF is equals to UF, then we will say function is Riemann integrable. But whether it has happened always or not, we don't know. But what we surely know is the following. Now, see here. So LF is what? Supremum of LFP. Okay, P is any partition of I. Also, UF is infimum of UFP. P is any partition of I. This both does exist. Okay, right. Now, right, let P1 and P2 be two partitions of I. Then P3, which is we are going to define as P1 union P2, be refinement of both P1 and P2. Okay, right. So what will happen is LF. So this implies LF P1 is going to be less than equals to LF P3, which is certainly less than equals to UF P3. And since P3 is also a refinement of P2, certainly it's going to be less than equals to UF P2. Okay, so this certainly tells you, I'm not using its P3 is a refinement of P1. So UF P3 is also less than equals to UF P1. Okay, but we want that for it is irrespective of any partition. So LF P1 is always less than equals to UF P2 for any two partitions of I. So this certainly implies this. So what it tells is this implies that UFP2 is always is going to be a upper bound for this LFP1. Okay, means you take any part. So this implies what we can say is okay. So you can always this is a question mark. Okay, you can say that okay that implies UFP2 is a upper bound of so UFP2 be an upper bound of the set of the set L of f of P such that P is any partition of I. Partition of I. It tells you that this is going to be an upper bound, but so this implies L of f is the supremum of this set. So L of f must be less than equals to U of fp. So now this is a number. Okay. And now you can vary this P2 now. Okay. So this will tells you that L of f becomes the lower bound of the set of UFP where P is any partition of I. So then by following the similarly, you can say similarly, one can show that, okay, let me go to the next page. So similarly, L of f is a lower bound of the set U of fp such that P is any partition of I. So it's a lower bound, and U, capital UF is a greatest lower bound, is infimum. Okay, so this certainly implies L of F must be less than equals to U of F. So what it tells is, this implies, if we write in the notation, the lower Riemann integral is going to be less than equals to the upper Riemann integral. So this inequality always hold. So whenever this two becomes equal, then we will say that F is Riemann integrable, and we denote it by, okay, we denote it by integration a to b f of x dx, that number value. Okay, right. So in case, if L of F is equals to U of F, is equals to U of F, we say that F is a Riemann integrable Okay, in other words, if you want to write the notation, okay, F belongs to this class of Riemann integrable over the set A to B. This is one of the notation you may see in the textbook, that R of with this closed interval AB is set of all possible Riemann integrable. So then F is Riemann integrable. Okay, that F is Riemann integrable, and that integration a to b f of x dx is defined as L of f or U of f. Okay, certainly you can question now, why started with first varying this, first I fixed P2 and then vary this P1. It is, you can do in the reverse manner as well. Okay, so you can fix P1 and you can vary P2. Okay, and show that LFP1 is becomes the lower bound for all the set of this. So this certainly LFP1 is going to be less than equals to UF. Then you can vary this P1. So you will get the similar expression. Okay, right. So when we function f is Riemann integrable. Okay, right. Okay, so this is about the Riemann integrable. Let's see. We have done all the things. Okay, so if I recall this lemma from the textbook, so it's very necessary to have a function to be Riemann integrable. We are only talking about the functions which are bounded on closed interval AB. Okay, we are not talking about a bounded function on an infinite length interval. That also, okay, it's like constant function, but the interval is unbounded, like on full on entire real line. We are not talking about that. We are only talking about the function which is bounded on a closed interval a to b, which is this closed and finite length. Okay, so this inequality is already established, that m times b minus a is less than equals to LFP less than equals to LFP less than equals to capital M. Okay, so this already done. Okay, further, if IF is bounded and P is any partition of I, that also has been done. LFP is always less than equals to L. Okay, if you consider the refinement that we have already, if P is Q is a refinement of P, this is a relation also hold that we have also shown. Okay, right. Okay. Now, we have also shown that the following, if let F is bounded and if P1 and P2 are any two partition of I, it is irrespective of that. So LFP1 is less than equals to LFP2. That we have also shown. By considering their union, and that will be the refinement of P1 as well as of P2 and use the previous result. Okay, and we have defined the following, that this is a lower Riemann integral, and this is the upper Riemann integral, which is we further denoted by this is going to be L of f, this is going to be capital U of f. These are the notation, and this notation is the class of all partition. Okay, it's like whenever you are taking any partition, it's going to belong to this set. Okay, so if this, so we have already established that LF is less than or equals to U of f. If they are equal, then we say that it is Riemann integral. Okay, so this already we have established. Okay, right. And this is a definition that just now we have already shown. So this A is either you obtain L of f or you obtain U of f. Okay, once you know that f is Riemann integrable, then either you obtain the lower Riemann sum or upper Riemann. So when I say this statement, when this statement is made here, every constant function is Riemann integrable, means we are talking about only the function which is defined on the closed and bounded interval by f of x is equals to, let's say, some c for all x in I. Okay, then you can certainly find out that what is LFP. So if you take any p partition here, so that is, let's say, x0, x1 and so on xn, any partition. Okay, so if you write down what is small m, mk is going to be infimum of f of x such that x belongs to ik. So f of x is constant, so it, on the ik also it takes all the values c, so this is equal to c for all k. Similarly, capital Mk, which is going to be the supremum of f of x such that x belongs to ik. So since it is here also f of x value is only, so what will be the supremum of the constant? Is constant c. So what is LFP? Is going to be summation small mk delta xk, where k is running from 1 to n, and that is equals to c time b minus a. Because mk is constant for every case, mk is c is out, and summation k equals to 1 to n delta xk is nothing but the length of the interval. Similarly, you can show that UFP is going to be summation capital Mk time delta xk, k is equals to 1 to n. Now capital Mk is also c for all k equals to 1 to n, so c is out, and summation delta xk is b minus a, so that is equal to c time b minus a. So you consider any partition here. So supremum, supremum of this set is still c time b minus a. Similarly, infimum of this set is still c time b minus a. Both are equal, so these are Riemann integral. Okay, so
Sir,
yeah,
would be enter into mind.
just where here.
Yes.
Let's okay. Let me write it here. So LFP, I'm just writing here. So similarly, you can follow the UFP as well. So LFP is summation small mk delta xk, k is equals to 1 to. Okay, so small mk is c, that you are agree, right? So small mk is c for every k equals to 1 to n. So c is there, so summation k equals to 1 to n, c time delta xk. Now c is independent of n or independent of k, right? C is independent of, c is a constant. So c times summation k equals to 1 to n delta xk. Okay, now what is delta xk? So c times summation k equals to 1 to n, delta xk is xk minus 1. Okay, now this is equals to c time So if you write k equals to 1, it is x1 minus x0. For k equals to 2, it is x2 minus x1 plus x3 minus x2 and so on, plus xn minus xn minus 1. So xn minus 1 minus xn minus 2 plus xn minus xn minus 1. Now it is easy to think that this x2, this all middle term will get cancelled. Only you will remain with xn minus x0, but xn is b and x0 is a, so c times b minus.
Okay, sir.
Okay, similarly you can go with the UFP as well. Okay, so similarly you have to open up. Now, so this is constant, it's a fixed number. Okay, so this is irrespective of any partition P. So this implies supremum of, or you can say LFP, where P is any partition of I is going to be still C times B minus A, because these are fixed. For any partition you take, is still C times B minus A. Supremum is still C times B minus A. And that is, you can have, this is L of F. And U of F is equals to, that infimum is going to be C times B minus A. Okay. And since they are equals, F is the Riemann integral, this implies L of F is equals to U of F. This implies F is Riemann integrable over the interval a to b. And what is the value of integration a to b f of x dx is c times b minus a, which is nothing, which is the same as that analytically you are trying to obtain, right? Okay. And integration a to b f of x dx is equals to either L of f or U of f, that is c times b minus a. Okay, which is same as what you, if you replace f of x equals to c and integrate, it's nothing but the c times length of the interval. Okay, right. So constant function is continuous function, right? It's differentiable, everything. So many nice properties are attached with it. What about different kind of function, like which is not even, means like continuous. Continuous is there. Okay. So consider the function f. Let's say this is a point function, you can say. At a point half, the value is 1, and elsewhere it is 0. Okay. So this function is certainly not continuous at x equals to half, that you can show. Right? So function is not continuous on the entire interval 0 to 1 equals. Okay. So this function is discontinuous at point x equals to half. Right? Okay. Now, what we want to show is f is Riemann integral. Still f is Riemann integral. Now, in this case, so you take any partition that is equals to, let's say, x0, x1, and so on xn. Okay? And ik is, what is there is xk minus 1, comma xk. Where k is equals to 1 to n. Okay, now let J is such that, okay, 1 by 2 is belongs to Ij. Okay, because these are non-overlapping subintervals. Okay, so half only can belongs to one of the interval. It will not belongs to two subintervals or others. So let the J is the index such that where half is this point is belong. Okay, now if I go with the definition, what is small mj? Oh, sorry, what is you can say, so what is mk? Mk is nothing but the infimum, right? Infimum of, you have f of x such that x belongs to ik. Now, so if k is not equals to j, function is 0. Still means entirely on entire. So mk is 0 for all k not equals to j. That's so sure. What about k equals to j? So for the jth interval as well, so f of only you have the f of half value is 1 and f of x value is 0 elsewhere on that interval. Okay. So but it is an infimum of that set. So still it is 0 only for all k. Right? Right. Now, capital MK, what can you tell about capital MK? So, capital MK by definition is infimum of, infimum, it's going to be supremum of f of x such that x belongs to ik. Now, this is equals to 0 if k is not equals to j. Because it is the function is 0 else everywhere else in the interval. Now, for if k is equals to j, somewhere the function value is at point half, and half is lies in the interval j interval, j sub interval. So at there, this is 1. Okay, so we have both the definition now, small mk and capital M. Okay, so before starting, so we can actually verify that this function is bounded. Okay, if the function is not bounded, it is we are not going to verify anything. Okay, because the Riemann integrability will not be applicable here in that case. Okay, but here function is bounded because at the max its value is 1 and at the means we can say minimum is 0. Okay, so it's bounded. Now, so this above by above definition, all this implies I can say for any partition P, the LFP is equals to small summation m small m k time delta xk. What is k is equals to 1 to n, and we know that small m k is 0 for all k, so that is 0. And about UFP. So UFP is equals to summation k equals to 1 to n capital Mk time delta k. Now it is Mk is equals to 0 if k is not equals to j, and it is 1 if k equals to j. So that is equals to delta x. Right. Now, so this is a UFP. So LFP is 0. So certainly that implies L of f is going to be 0. That's supremum of the zeros or 0. What about capital UN? That infimum of UFP, where P is any partition of partition of I. Note that this delta xj is nothing but the length of the jth subinterval. These are always non-negative. So this is always greater than equals to 0 for all j. Any means if you fix j, it is still always greater than equals to 0. So show that. So I can give you the hint and that you can verify that that is actually 0. Why? Because if you take this is the infimum. Okay. So if you take, let's say infimum is w. Okay. Let's say w. Okay, and which is certainly greater than equal to 0, that we know, because this is UFP. This 0 is a lower bound for every partition P. So this W is greatest. So W is greater than equal to 0. That's for sure. Now you can discard the fact that W is strictly greater than 0. How? If you take W greater than 0, let's say, then you can create a new refinement of the partition by subdividing the interval with the length W by 2. Okay, and that will show that the W is not an infimum. W by 2 is still in the set. Okay, because UFP is nothing but the delta xj. Okay, so you can discard the fact that W can never be greater than 0 by the appropriately choosing a new partition P such that whose jth subinterval length is w by 2. Okay, where the half is belonging. Okay, then your assumption is wrong. So then you can have it certainly equals to 0 only. So that you can work out easily. Okay, so this function is discontinuous at one point. Okay, but it is still Riemann integrable. Okay, so there is a result, okay, that you will maybe soon learn, that if a function is continuous everywhere on the closed interval AB except at finitely many points, means it is only as a finitely many point of discontinuity. So this is a one point of discontinuity there. So in this, so similarly, you can have the finitely many. You can extend this result to the finitely many point of discontinuity. Means you can instead of half, you can have the means half 1 by 4, 1 by 3 by 4, 1 by 3, and so on. So finitely many points are also you can take where the function is discontinuous. So still you can prove that the length that function is going to be Riemann integral. Okay, right. So that is going to be the result.
Sir,
you can say. Yeah.
Can you explain why small mk is equal to 0?
Small mk is 0. Yeah. Okay. See, small mk is what? By definition, infimum of f of x such that x belongs to I. Now, you choose any ik subinterval. So, except k equals to j, let's say k is not equals to j. For the k not equals to j, f of x is 0. So, all the values are 0. F is vanishing over all the intervals except if only k equals to j. Do you agree with this?
Yes, sir.
Definition. Okay. Now, in the jth subinterval, let's say where it is taking a non-zero value. Okay. So, see, this f of half is positive value 1. Okay. If it is a negative value, then mk is minus 1. Okay. So, you see, f of half, so it will take in the interval ijth subinterval, all the values are 0 except at half value is 1. Do you agree with this?
Yes, sir.
So this set will take the values either 0 or 1 right now. Okay, so I can form this set 0, 1. What is the infimum here is 0, irrespective of any k. Infimum means when you have the finite set, it is a minimum. Okay, so what is the minimum among 0 and 1 is 0.
0. Okay.
Similarly for the capital M. So okay, so if you replace 1 by minus 1 here, then small mk becomes the minus 1 instead of 0. Because we are not taking here magnitude. Okay, so if you take here 2, 3, 4, so still minimum is 0, infimum is 0. If you take negative value, it is going to be negative. Okay, right?
Okay, sir.
Okay, right. Now the next, yeah.
So why we don't take 1 as a supremum, and why we do two conditions there?
Where?
Yeah, in the supremum. Yes, here. Why we take two conditions here? We can't take 1 as a supremum. Yes,
this mk is for, mk is, you have to check for each subinterval, no, k equals to 1, 2, 3, and so on, n. Okay, so for mk value, whenever k is not equal to, so j is somewhere in between. Okay, so before this and after this, mk is 0. Okay, because you have to fix capital M1, capital M2, capital M3, and so on, capital Mn. Okay, so capital M1 becomes 0 because whenever j is not equals to 1, suppose j is equals to 1, then M1 becomes the 1, then other M2 to Mn becomes 0. If j is equals to 2, let's say j is equals to 2, Okay, so then M1 becomes 0, M2 becomes 1, M3 becomes 0, and so Mn becomes 0. Did you get it?
Yes, sir.
Okay, thank you. Right. Right. So this certainly tells you that L of f is equals to U of f, and that is equals to 0. And this certainly tells you that integration 0 to 1, the given function f of x dx is equal to that same. That point function does not have any area, right? So you can also verify this. Yeah.
In the previous slide, what is delta xj?
Delta xj is the length of the subinterval jth subinterval. So xj is xj minus xj minus 1.
Okay.
Okay. Right. So what we have observed is, for this case, integration 0 to 1 f of x dx is 0. Okay, right. Now the next result is saying that not every bounded function is Riemann integrable. So that will prove that the boundedness of the function is not a sufficient condition. Okay, it's only a necessary condition. Okay, for example, you can take this Dirichlet function, and Dirichlet function is many times is coming into the picture for giving the contradiction proof for some many things. So if, let's say, x belongs to 0, 1 intersection with set of rational numbers, and 0 if x belongs to 0, 1 intersection with set of irrational numbers. You know that this function is not continuous, right? The function is nowhere continuous. Okay. Yeah, so this function is not every bounded function is Riemann integrable. So for this case, what you can show, so I can give you that to verify that LFP for any partition, that LFP becomes 0 and UFP becomes 1. Okay, so that's very easy to show, because every so you are going to apply the density theorem here. Between any two real number, there is always a rational number as well as an irrational number. And if you are going to calculate small mk, that is going to be 1. Sorry, that is going to be 0 for all k, because that's going to be infimum over f of x such that x belongs to ik. Okay, but ik, every sub-interval will contain rational number as well as an irrational numbers. Okay, so the values are 0, 1. Okay, so for each mk, for each k, m1 if you take or m2 you take, that value is 0. Similarly, you can show that capital mk is going to be 1 for all k. Okay, that can be shown because every between any two real number, there is always an irrational number. So you take any sub-interval ik. So ik will contain infinitely many. So ik will contain infinitely many sub-intervals. Okay, so sorry, ik will contain infinitely many irrational numbers as well as rational numbers both. So in this ik, the value of function is either 0 or 1. So it can take either 0 value as well, and the function somewhere will take the 1 value as well. So what is the supremum is 1. Okay, so mk can be shown that is equals to 1 for every k. Small mk can be shown that is equals to 0 for every k. And then if you write down LFP, so small mk is 0 for all k, so that will turn out to be 0. UFP is equals to summation capital mk times delta xk. So capital mk is 1 and summation, so mk is 1 for all k, and summation delta xk is nothing but the length of the interval, that is nothing but the 0 to 1 interval length is 1. Okay, so that can be shown that EFP is 1. So now you can see in the limiting case, so LFP is 0, so that you can show that this also implies that lower Riemann integral is 0 and upper Riemann integral is 1. So where equality will not occur, so that function is not Riemann integrable, though it is bounded. Okay, right. Okay. Now, now one more result is there, that so you have the Thomas function and you have the signum function. So composition of two Riemann integrable function is let's recall this Thomas function. What is the Thomas function? So h from close interval 0, 1 to r is defined as h of m by n is equals to 1 by n. Okay, whenever you have this m comma n belongs to set of natural number, okay, and that GCD of m comma n, that greatest common divisor is 1, and it is equals to h of x is equals to 0 elsewhere. Means you have the rational number, okay, and you got elsewhere means at irrational numbers. Okay, so rational numbers are all of the form of p by q. Okay, so this certainly is a bounded function. Okay, whether it is Riemann integrable, that you have to show. Okay, so it can be shown that h is Riemann integrable. Okay, so let you have this is x naught equals to 0, x1 equals to 1 by n, x2 equals to 2 by n, x3 equals to 3 by n, and so on. So xn minus 1 is equals to n minus 1 by n, and xn is equals to n by n, that is equals to 1. Okay, now on this intervals, now you can check whether the function, so 1 by n is certainly less than 2 by n, 2 by n is certainly less than 3 by n, and so on. Okay, and you can certainly tell the function is increasing over this. Okay, and then you can certainly talk about the infimum and supremum over this set. Okay, so over this partition now. Okay, so what is ik now? This implies ik is equals to, you have this is k minus 1 by n to k by n. Okay, so this implies small mk is going to be 0 for all k. That's so sure, because it assumes 0 values as well and some other rational, so that's certainly going to be 0 infimum. Now, what about capital Mk, that is equals to supremum of f of x such that x belongs to ik f of x, or you can say h of x here. Okay. Now it will take either 0 values, and you see it's in between any, you can take any rational numbers. So it's going to be the supremum at the right hand point of the interval, that is going to be h of k by n, right? So that is going to be 1 by n for all k, you can say. It is irrespective of any value. Yes, so this will imply that L of fp for this case which will be is equals to 0. And what about UFP is going to be, if you write the definition, small capital Mk times delta xk, k is equals to 1 to n, capital Mk is 1 by n, delta xk is 1, so that is 1 by n. So if you increase number of points, so that 1 by n will certainly decrease, and or you can say the supreme that infimum of this set, we have already shown that infimum of 1 by n such that n belongs to natural number is 0. Okay, so this certainly implies that L of f is 0, and L of f is 0 because supremum of the set 0 is 0, and capital U of f is going to be infimum of 1 by n such that n belongs to natural number, and which we have already shown that that is 0. So this shows that L of f is equals to 0 and U of f is equals to 0. So this shows that L of f is equals to U of f, and hence this implies that f is Riemann integrable, but you can say this is f, instead of f we have the h here. Okay, so we can just rewrite the notations here. Okay, so see, we have seen previously we have considered the random any partition P. Now here we are considering the sequence of partitions. Okay, so whether both are the same thing or not, that will be given little later. Okay, right? And I can tell you the conclusion means either you work with the sequence of the partition or you work with the random partition. Both are going to be the same in terms of Riemann integrability criteria. So this shows that the Thomas function is Riemann integrable. Okay. Now, what about the signum function? So signum function is defined as signum function. If you define on the interval, let's say 0, 1 to r only, is defined as, you know, signum function of x is going to be mod x by x. Yeah, is equals to 1 for all x belongs to open 0, 1, and it is equals to 0 for x equals to 0. So this is continuous everywhere except at x equals to 0. So this is going to be, so you can verify that this function is going to be Riemann integrable. That also you can verify by looking at the same fashion. You have to go in the same fashion as you have done for that point function. Similarly, you can work with here also. So both functions are Riemann integrable. Okay. Now, what we need to verify is that composition, their composition, signum function of h. So what will be the signum function composed with h? That is equals to signum function of h of x. Now, this is equals to 0 if h of x is 0. Okay, if h of x is not 0 means it is of the form of, so h of x is not 0. There are two possibilities, either h of x is 0 or h of x is not 0. Okay, so if h of x is 0, it's 0. If h of x is not 0, it is going to be 1. Because if because when x is not, when for which value of x it is non-zero, if it is of the form m by n, and it is of h of x, h of m by n is 1 by n, which is positive, right? So 1 by n is belongs to upper 0, 1. So you can certainly take 1, and which is Dirichlet function, right? This if means like this is what it means, that x belongs to 0, 1 intersection with set of rational numbers, and this is x belongs to 0, 1 intersection with set of irrational numbers. So which we have already shown that this is not a Riemann integrable. So composition of two Riemann integrable function is need not be Riemann integrable. Okay. Right. So, right. So so now what I can give you the exercise now is as follows. Okay. So you can now work out with this exercise. The very first exercise is f belongs to f is Riemann integrable. Okay, and let C belongs to the open interval AB. Any point. Okay, let C belongs to open interval AB. Okay, then F is belongs to Riemann integrable over the interval A to C, and F is also belongs to Riemann integrable over C to B. Okay, and integration A to B f of x dx is equals to integration A to C f of x dx plus integration C to B f of x dx. Means the breaking point. Okay, so you take that, see, whenever this is the same thing, means like you have the partition of AB. So each ik, the function is Riemann integrable. Whenever the function is Riemann integrable over the I. And it is if and only if actually. Okay, so converse also exercise 2 is converse of above will hold, will also hold. True. Means if f belongs to the f is Riemann integral over the interval A to C, and f is Riemann integral over the interval C to B, and C is the point in between A to B. Okay, then that function is Riemann integrable over the entire interval A to B. So this is if and only if condition. So this you can generalize to now any finitely many points you can now, okay, it means like suppose a x1 x2 x on, so then you can make it the interval break. So integration a to x1 plus x1 to x2 plus integration x2 to x3 and so on. Okay, and you can now certainly shows that exercise 3, if f belongs to the Riemann integrable is a Riemann integrable, then integration a to b f of x dx is equals to summation I is equals to 1 to n integration xk minus 1 to xk f of x dx. Okay, so you find out on this each subinterval the integral and then sum up. That's the same thing as integration over the entire interval a to b f of x. And this will be useful when you are only knowing about the behavior of the function f. Means it is increasing in between the interval xk minus 1 to xk, and it is somewhere decreasing and so on. Okay, so this will help you to approximate the integral values whenever the function is not means you cannot find the antiderivative of. Okay. Similarly, you can show that if f is Riemann integrable, then its scalar multiple function is also Riemann integrable. Okay, so from above it is immediate. These are immediate results. Okay, so that you can verify. So if f belongs to the Riemann integrable AB, then C time f also belongs to Riemann integrable. Is a Riemann integrable, and integration a to b c time f of x dx is going to be c time integration a to b f of x dx. So if f belongs to Riemann integrable, then you can show that mod of integration a to b f of x dx is less than equals to integration a to b mod f of x dx. So these are all our immediate exercises. Like you have to play with the LFP and UFP. Okay, right. So here we end today, and then the next we are going to use very important results known as fundamental theorem of integral calculus, and then we are going to bind up this Riemann integral by giving that numerical approximation. Okay, so it actually leads to the numerical approximation to the integral as well, and we use the idea of the Riemann integral there. Okay, that it is approximating the area by means of rectangle. So then we try to approximate the area by using other means like trapezium, that will lead to the trapezoidal rule, by using the quadratic curve, by using 3 points at a time, that will lead to the Simpson's 1/3 rule, which you have the part of the process. Okay, so in the next session we are going to get those details. Okay, thank you.